Welcome. As is the name of the podcast, we start with thinking about a problem or opportunity, which is the first episode for any topic. Then we build the product in the second episode. And on the third episode, we talk about how to scale a company using that product. This is the second episode for the topic of a satellite system to be used exclusively for fueling Europe's big data and AI roadmap. That means we will build the satellite in this episode. If you want to understand more about the background of this topic, please go to the first episode. There are many terms which you might not understand, so it would be very helpful if you go to the first episode and start from the beginning of this series. The next episode will talk about how these satellites are scalable products and how they will continue to generate wealth for the European Union for ages to come. However, that episode will be with a twist. We will talk more from the perspective of a supplier of the ESA, how they can scale their company. And why are we going to talk about it? Before I proceed, I want to mention that no NDA has been violated during the making of this video or any of the videos in my podcast so far. In the previous episode, we were conceptualizing a satellite named HCOIS that would serve as a deliverable for the Hydron project of European Space Agency. In this chapter, we will talk about building the product. As we always do, we break the system down. For the topic of a transmission electron microscope, I have previously given the example of a human body and the various systems present within the body. It's going to be the same thing here or similar here. The satellite itself would be called the system in concern. And then there would be multiple subsystems like the payload, bus, communication and controls, ground interface, etc., etc. Okay, in simple terms, all these subsystems are networked through central nervous system, usually managed by the onboard computer, OBC, with dedicated data buses, power lines, and control signal channels connecting everything. So you think of it like a human body. Your onboard computer is your brain, your data buses are your nerves, the power supply is your blood supply, equivalent to a human body. And then the structure of the structural components of the satellite system would be the skeleton system of the human body. The thermal and HCOIS, etc., are the internal organs managing the environment and balance, just like a human body. So wait a minute, a machine is nothing but a series of functions to be performed by a combination of components talking to each other at a given point of time. I have mentioned this in my previous talks as well. Let's look at that properly. How exactly are these systems communicating with each other? So you have functions on the left side. You will see functions like command and control, data transport, power distribution, thermal management. These are all functions. The attitude and orbit control, HCOIS, downlink, modular interfaces. These are all functions. These are all things that are to be done by the satellite, by the machine itself. It's interesting. For command and control, what's exactly happening here? The onboard computer, OBC, acts like the satellite's brain. It sends instructions and collects status information from all other subsystems. So OBC talks to all other subsystems, basically. For data transport, high-speed payload data, especially from the optical terminals, flows first into the OBC, which then routes it to the RF communication system to send down to Earth. So payload talks to OBC, which talks to RF module, and then RF module talks to OBC, and then payload. The power distribution. The power distribution system supplies electrical energy to every part of the satellite. It also monitors if parts are getting the power they need. So the power system talks to all subsystems, just like the OBC. And of course, the power system connects all subsystems anyway, maintains a relationship with the OBC anyway. Thermal management. The thermal system keeps everything at the right temperature. It senses heat levels across the payload, the bus, and adjusts heaters, coolers, or radiators as needed. The thermal system connects with the OBC and vice versa. Then you have the OBC, the payload, and the bus as well. And all of these systems also directly connect with the thermal system in return. Attitude and orbit control, AOCS. Sensors like gyros and star trackers tell the OBC how the satellite is oriented. If the OBC then commands motors or thrusters to adjust the satellite's position, keeping the optical payloads pointed correctly. So the AOCS sensors and actuators talk to OBC, which in turn talks to payload. And then the way back is also possible, payload to OBC and then to the actuators and sensors of the AOCS. Ground link function. The satellite communicates with the ground stations through its RF systems. Commands from Earth reach the OBC, and health data and mission data are sent back to Earth. So OBC talks to the RF module and then the ground station. The ground station talks to the RF module and then OBC. Modular interfaces. Some parts, like the optical terminals, can be swapped. When new hardware is plugged in, quick connect interfaces automatically notify the OBC that a new module is online and ready. So quick swap interfaces talks to OBC and then vice versa. Let's talk subsystem by subsystem. The first subsystem I want to discuss is the payload subsystem overview. The main function of the payload subsystem for Hadron class optical interconnect satellite, which is HCOIS, would be to be designed primarily for high throughput optical communication and all optical switching of data streams between satellites, ground terminals, and future space infrastructure. It could enable terabit scale data relay with low latency and high resilience, supporting both classical and quantum communication technologies. The major modules and their potential roles. So obviously the payload system would have the optical terminal assemblies, it would have the photonic switch assembly, and then it would also have an optional quantum module. The optical terminal assemblies, let's talk about that module a little bit. The optical terminal assemblies would serve as the satellite's external communication interface, enabling precise transmission and reception of optical signals across space and atmosphere. You can see a concept of it. This is not far from being the final CAD or anything. This is just a concept. The optical telescopes would be gimbaled or fixed. Here is just a gimbaled one. They would be used to focus incoming beams and collimate outgoing beams over long distances. Some versions might be gimbaled to allow dynamic pointing and tracking of fast-moving targets, while others could be fixed for simpler, cost-effective deployments with narrower fields of view. Beam steering mirrors. Beam steering mirrors could provide fast course alignment of the optical beam without the need to reposition large telescope assemblies. This would reduce mass and response time for pointing adjustments. And then you have your fine pointing assemblies. They would offer micron or submicron level correction capabilities, ensuring that the optical links remain tightly locked even when the satellite experiences small mechanical or orbital. FSM, which is your fast steering mirrors, could be incorporated to deliver high frequency jitter correction, compensating for rapid spacecraft vibrations or disturbances, and maintain beam stability during data transmission. Your optical benches, which are thermally stable platforms. These are precision optical benches, and they would house critical optical components. These benches could be thermally stabilized to minimize expansion, contraction, or warping due to temperature fluctuations in orbit. Generally, they're also with high CTE. They're made out of high CTE material. Laser sources and beam expanders. Laser sources may be installed to generate coherent light signals, possibly operating in wavelengths suitable for deep space optical communication. Beam expanders could enlarge the outgoing beam diameter to minimize divergence across intersatellite and Earth space distances. Adaptive optics modules. Adaptive optics modules could be incorporated to correct real-time distortions in the optical wavefront caused by atmospheric turbulence or internal optical path errors. This would typically involve deformable mirrors adjusted based on feedback from embedded wavefront sensors. Fiber couplers could be used to efficiently transfer free space optical beams into the onboard fiber optic network for routing and processing without significant signal loss. Photonic switch assembly. The photonic switch assembly would represent the core of the satellite's all-optical routing capability, minimizing latency and power consumption compared to traditional electronic switches. The photonic switch elements, which are photonic integrated circuits, circuit mounts, could be based on PIC mounted on vibration-dampened platforms, ensuring stable optical routing performance even during minor spacecraft disturbances. The thermally controlled racks for PICs. Dedicated racks with active thermal regulation could house PICs, maintaining them within right temperature limits to ensure operational stability, reduce space drift, and optimize optical switching efficiency. The optical connectors and routing fibers, a network of ruggedized, radiation-tolerant optical connectors and fibers could be implemented to interlink the terminal assemblies with the switching modules and ensure high-reliability data transport across the payload. The vibration isolation platform or mount could protect the delicate photonic switching elements from mechanical shocks, ensuring continued precision performance over the satellite's operational life. We talked a lot about this topic, the precision and vibration. How is precision and accuracy connected to vibration isolation and then passive damping or active damping of these vibrations? Go and check out the very first, the second episode I made for the series of transmission electron microscope, because that's also an optomechanical system. And I showed how a small amount of vibrations, every minute amount of vibrations need to be controlled and damped and eliminated for accuracy and precision purposes. Now, how does that happen? So when we are talking about systems like these, where you have very micrometer, nanometer level features in different components, because of heat and because of any other physical vibration, even if the component moves even 1 micron or 1 nanometer, that could lead towards a problem within the data transmission that could disrupt the flow of the laser beam or the path of the laser beam. So that's why vibration isolation is extremely important in areas like this, in applications like this. Quantum module, let's talk about that. An optional quantum module could be added to enable quantum key distribution capabilities or prepare the system for future quantum networking applications. The QKD optical benches. These optical benches would be purpose-built to handle quantum-grade optical elements, supporting tasks such as entangled photon generation, single photon transmission, and precise polarization control. Single photon detectors with thermally regulated housings, they are ultra-sensitive single photon detectors, and they would be included to receive extremely weak quantum signals with thermally regulated housings to minimize noise, dark counts, and environmental interference. Quantum optics isolation cages. These quantum-specific optics could be enclosed within dedicated isolation cages designed to block stray light, mechanical vibrations, and external electromagnetic fields, ensuring maximum integrity of quantum communications. All right, so overall, the payload subsystem of the Hydron class optic interconnect satellite could be a highly modular, flexible assembly of integrating advanced optical communication terminals an all-optical photonic switch, and optional quantum-ready modules. It would be engineered for interoperability across low Earth orbit, medium Earth orbit, and geostationary Earth orbit systems, aligning with Europe's strategic ambitions for a sovereign, space-based optical backbone in the AI and quantum era. Let's talk about the bus subsystem now. Remember, we were going from subsystem to subsystem. So think of the bus as the service body of the satellite. It supports the mission equipment, the payload, and keeps the satellite alive in space by providing power, temperature, control, structure, and steering. I'm naming it a bus because just like a city bus carries many passengers while providing wheels, fuel, and protection, the satellite bus carries payloads while providing energy, direction, and structure. All right, there are 4 modules within the bus subsystem: the primary structure module, the power system, the thermal management, and attitude and orbit control system, AOCS. Primary structure, which is the load-bearing skeleton. This framework is generally made out of carbon fiber trusses and aluminum panels. It's strong but very light, helping survive launch forces and keep everything rigid in space. And the equipment mounting panels are generally flat, strong surfaces where instruments, computers, and tanks are bolted down securely. You also have folded arms that can extend outward after launch if a payload like a laser needs to be far from the main body to work better. Now, let's go to the second structure module, which is the internal support and shock protection. So, smaller supports inside, you have internal bracketing. That is the smaller support that holds lighter or delicate equipment firmly. They are shock absorbers that protect sensitive parts from shaking during the launch and small vibrations in space. And of course, you have isolation platforms. There are special floating plates for very sensitive optics or instruments so they don't get disturbed even by tiny movements. The power system, it collects energy and stores it. Quite simple. So solar array drive mechanisms, motors and hinges that unfold the solar panels after the satellite reaches space and keep them pointing at the sun for maximum energy. Battery mounting cages are strong frames that safely hold the batteries. And heat sinks, of course, are for power electronics. These are metal plates or tubes that pull away heat from batteries and computers to prevent overheating, just like every other high-power electronic system. Thermal management. They are to keep everything not too hot and not too cold. You have the radiator panels, big shiny surfaces that throw away extra heat into space. Heat pipes and loop heat pipes. Tubes filled with special fluids that move heat from hot parts of the radiators using only a passive flow. These are special fluids, they're nothing but metal, actually. Cryocoolers, they are mini refrigerators that super cool sensitive equipment like optical sensors and lasers. You have the multi-layer insulation blankets. These are thin, shiny space blankets that are wrapped around the satellite to trap heat inside or block heat from the sun. That takes us to our 5th module of the bus subsystem, which is the attitude and orbit control system. So structures, so you have points and so you have reaction wheel mounting frames. These are structures that hold spinning wheels. By speeding up or slowing down, these wheels rotate the satellite very precisely. Star tracker mounts, secure mounts for small cameras that look at stars to figure out exactly where the satellite is pointed. Gyroscope housings are protective cases for gyros that measure rotation movements. And then you have fine pointing actuators, which are piezo-driven stages. They are tiny motors that make superfine adjustments needed when aiming lasers or cameras very accurately. Thruster brackets, they hold small rocket engines, which are called thrusters, that push the satellite slightly to fix its orbit or move it a little. So let's recap once again. For the bus subsystem, You have, imagine that the satellite is like a high-tech drone flying in the space. Primary structure, it's skeleton. You have the secondary structure, the internal shock absorbers. You have the power system, which is your solar fuel system. You have your thermal system, the heating and cooling gear, and you have AOCS, its steering and aiming system. All of these are part of the bus subsystem and make sure that the payload, your lasers and antennas, your cameras, can do its mission perfectly. In the design of the HCOIS, Hydron Class Optic Interconnect Satellite, the compute and edge processing subsystem is the onboard brain of the satellite. So here is what it does. The AI accelerator or edge processing system, the satellite needs to make decisions on its own in real time. It can't always wait for a command from Earth. Radio delays, network congestion, or emergencies might make that quite impractical. So instead, it uses AI accelerators, which are special processors optimized for AI tasks to prioritize what data is important, compress data smartly to save bandwidth, route data efficiently through optical links. Example would be, imagine there is a natural disaster like a major earthquake detected through Earth observation satellites. Rather than waiting for operators on Earth to tell it what to do, HCOIS can immediately prioritize sending evacuation maps, emergency communication streams. It delay or compress less critical data like routine monitoring reports. Your space-grade processors. Normal computer chips cannot survive space radiation. They would glitch or they would fail. So the satellite uses radiation-hardened processors like FPGAs, field programmable gate arrays that are reprogrammable and robust against radiation. Neuromorphic chips, future-ready, that mimic the brain style of computing for fast, low-power decision-making. These processors allow the satellite to operate in a smart, event-driven way, reacting intelligently to changing conditions without needing constant micromanagement from human operators. In short, HCOIS does not just follow pre-written scripts. It thinks and adapts on its own, securely and reliably, even in deep space for high radiation environments. The next subsystem is your ground interface subsystem. The main function would be responsible for safe handling, transport, integration, and operational preparation of the HCOIS satellite during its journey from clean room to orbit. This subsystem could be conceptualized as the interface layer between the satellite and all Earthbound infrastructure. It must interact with cranes, test benches, transport containers, environmental conditioning systems, and the launch vehicle itself. Its design would prioritize structural integrity, contamination control, and vibration isolation, especially given the optical precision and photonic sensitivity of HCOIS. Modules and their hypothetical roles. The launch adapter module. This module would likely serve as the mechanical bridge between HCOIS and its chosen launch vehicle. Depending on the orbit, the LEO, MEO, or GEO, modularity in the adapter design could allow for reuse across different launch configurations. It could feature a standard interface ring like RUAG pass, RUAG pass, or ESPA class mount, but might also require custom machining or inserts to align with the mass and center of gravity constraints of the payload. Separation system structure. So the HCOIS could be equipped with either pyrotechnic release devices such as clamp bands with explosive bolts or non-pyrotechnic spring-loaded separation systems for smoother reusable decoupling. This structure would be responsible for holding the satellite securely during ascent and then cleanly detaching it into orbit at the correct insertion vector. Design choices here would likely depend on mission reliability criteria, debris minimization strategies, and whether the reusability or inspection friendliness is prioritized. Your launch vibration isolators. To protect your sensitive optical terminals and photonic switch fabrics, this subsystem would almost certainly include a vibration isolation mount or dampers, perhaps integrating elastomeric pads or tuned mass dampers. Ground support equipment interface. This subsystem could include standardized docking features, alignment pins, or structural interface plates that allow the satellite to be safely manipulated using ground support equipment GSE, such as hoists, cleanroom transporters, and vertical integration towers. These interfaces might also double as static discharge grounding points, ensuring electromagnetic safety during fueling or electronic servicing. The lifting points and features. HCOIS would be designed with strategically located lifting lugs or points to accommodate crane hooks or robotic arms for handling during integration. These fixtures should be retractable or removable, especially in designs where low aerodynamic profile or mass reduction is critical. Now, for electrical and optical test ports, during ground operations, engineers would require diagnostic access without breaching the clean internal compartments. Therefore, HCOIS could feature removable access panels leading to electrical test ports for subsystem verification and software updates. You have your fiber optic loopbacks or patch bays for checking alignment, attenuation, and routing integrity. And these access points would be sealed against contamination and might be designed to remain accessible even when the satellite is on the launch pad. Environmental control system interfaces. To maintain operational readiness, especially for temperature and humidity sensitive components like lasers and photonic chips, HCOIS would likely interface with external environmental control systems like the ECS. This might include purge points for dry nitrogen or clean airflow, thermal regulation inlets for maintaining payload temperatures within acceptable pre-launch limits, humidity and particulate monitoring interfaces possibly linked to cleanroom compliance sensors. Why does subsystem actually matter? In this context of a high throughput optical backbone satellite like HCOIS, the ground interface subsystem would play a very crucial role because it preserves payload integrity and ensures mission readiness. Its modules would have to balance structural ruggedness with delicate handling, ease of access with contamination control, and mechanical compatibility with multiple launch environments. The data routing security. There would be a dedicated optical data path in space that could be used exclusively for European data, ensuring no one else could intercept or monitor it. You have it as a cryptographic key management, so all access and operations would be protected by cryptographic keys that could be controlled and solely accessed by ESA. And your quantum encryption compatibility of the system would be to support future quantum secure communications, and it could be added later to make data transmission virtually unhackable. Modularity and upgradability mechanisms. The goal would be to enable future-proof upgrades and repairs in orbit or when it has arrived in the ground, minimizing downtime and maximizing mission lifespan. This design philosophy would ensure that the satellite can evolve alongside advancing technologies. So your terminal quick swap interfaces. These would be dedicated interfaces allowing optical communication terminals to be swapped in or out without altering the entire satellite structure. Example, if a new optical terminal standard is released by ESA or an international partner, example, higher power ISLs with new wavelength bands, the satellite could be upgraded by simply detaching the old terminal from its quick swap interface and docking in the new one, using a standardized mechanical arm or robotic servicing unit. Design feature. This interface would include standardized mechanical and docking rings and quick release connector blocks for both electrical and optical inputs and out. Think of it like a USB-C port for space hardware, but ruggedized and built for robotic handling. Photonic payload bay. This would be a dedicated internal section within the satellite bus that houses all critical photonic components like switch fabrics, filters, multiplexers, etc., in a way that enables easy access and replacement. Reconfigurable optical bells. These could be slide-in modular racks that hold all optical switching components, such as a photonic crossbar or wavelength selective routers. If ESA develops a better photonic switch technology, example one with lower insertion loss or better channel granularity, the old bench could be slid out and the new one slitted with minimal rework on the rest of the system. The standardized mechanical frames would hold the optical benches in place and maintain alignment. These could be built to standardized sizes and mounting hole patterns, so future vendors or ESA labs can pre-design compatible modules without needing to re-engineer the entire satellite layout. The HCIOS satellite would be built with built like a high-performance server, where optical terminals and payload components could be hot swapped or upgraded during its operational life. Designed for space. Now comes the fun. So far, whatever you have seen isn't that special, actually. You can look at it as a machine that is holding up an electronic system for receiving, storing, and releasing data through laser beams. That's all. There's nothing special about it. We have to send this machine up into space. We have to look at three very important considerations: radiation, space debris and micrometeoroids, and your general environmental conditions like temperature and vacuum. We will go subsystem by subsystem and see how to optimize each subsystem, each module, and each component. Payload subsystem optimized for radiation, space debris, and extreme temperatures and extreme vacuum. The optical communication modules. The optical transceiver units would be the beating heart of HCIOS, responsible for sustaining terabit class links across space. These units could be protected from galactic cosmic rays and solar particle events using radiation-hardened photodiodes and shielded laser drivers, while tantalum plating or other dense localized shielding would reduce single event upsets. To withstand micrometeoroid impacts, optical apertures may be backed by Whipple shield geometries, ultra-thin sacrificial layers that fragment incoming particles before they reach critical optics. Additionally, redundant optical heads spread across the spacecraft body and would ensure that a single impact wouldn't cripple communications. Thermally, these optics would likely need active cooling, especially for the fine beam steering mirrors and deformable optics. The thermoelectric coolers paired with loop heat pipes and radiator panels could be used to maintain phase and beam stability despite the intense sunlight darkness temperature swings of orbital operations. Optics would be coated with gold or silver reflective layers, not just for performance, but to resist atomic oxygen erosion in LEO and to reduce charging risk. Your photonic switches and routing. This photonic crossbar switch, core to all optical routing, could use radiation-hardened silicon photonics or 3-4 class 3, class 5 photonic ICs, ensuring minimal impact from bit flips or ionizing damage. The MEMS-based tunable filters and switches may be fabricated with silicon on insulator technologies for improved radiation resilience. To deal with impact hazards, these tiny optical elements could be encapsulated in hermetically sealed, shock-dampening casings, while internally the switching fabric may support redundant routing paths to quickly isolate damaged segments. Given their thermal sensitivity, these photonic circuits could benefit from phase change materials for passive buffering, along with heat pipes that interface to platform radiators. The entire assembly could be vacuum sealed and conformally coated to prevent outgassing contamination. Your quantum communications module, which is a bit optional, by the way, for future quantum relay capability, single photon detectors like SNSPD, superconducting nanowires would require cryogenic cooling and hence multi-layer insulation-clad cryochambers. These chambers could be built with internal vibration damping to handle launch loads and debris microshocks. To protect from space radiation, these detectors would be enclosed in layered radiation shields, and optics leading to them might be restricted to narrow, hardened apertures. The external interfaces like your QKD downlinks would need anti-static coatings and anti-reflection layers resistant to AO erosion and thermal cycling. Your platform subsystem. Now, how is that customized for space? Solar arrays, likely based on triple junction gallium arsenide technology, are inherently radiation tolerant, but still degrade under prolonged GCR-SPE exposure. Cover glasses doped with cerium oxide could provide enhanced resistance, while segmented power strings would allow continued function even after partial impact or degradation. To mitigate debris, array panels might include flexible backplanes with Kevlar reinforcement, preventing a crack from propagating. Onboard batteries would be housed in thermally insulated shock-resistant modules with SEL immune power conditioning circuits to handle radiation-induced anomalies. Powering all of this is a suite of solar arrays, like triple-junction gallium arsenide cells chosen for their high efficiency and radiation tolerance. Over time, radiation will degrade them, but this could be slowed with cerium-doped cover glasses. Structurally, they would be flexible but rugged, perhaps reinforced with Kevlar mesh to survive micro-impacts without tearing across entire array. Inside the bus, attitude control systems would be mounted on isolation platforms. Redundant star trackers and gyros hardened against single event upsets would ensure HCOIS can keep a steady lock even after a burst of solar particles or a minor shock wave from nearby debris impact. Heat. Heat is a constant negotiation in space. HCOIS would juggle intense hotspots from high-power lasers with cryogenic zones for quantum detectors, likely using a hybrid thermal system of loop pipes, PCMs, and surface coatings optimized for LEO orbits. For the ADCS, the Attitude Control Unit, critical sensors like star trackers and gyroscopes could be mounted on vibration isolation benches inside the central bus. These sensors would employ redundant units and radiation-tolerant firmware to recover from SEUs, while components like reaction wheels would be designed to reduce microvibrations that could disturb precision optical links. During design, the entire ADCS suite would be analyzed for thermal deformation and modal shifts. The thermal management. A hybrid thermal management approach, combining loop heat pipes, radiators, and phase change units. It could be used to balance the needs of high-power lasers, cryogenic systems, and sensitive electronics. These elements would be degassed fluids and vacuum-compatible interface materials and can be covered in optical white paints or anodized surfaces to fine-tune radiative properties. Your compute and control system. The HCOIS would rely on space-grade FPGAs and neuromorphic co-processors for onboard AI and switching logics. These systems would be hardened using triple modular redundancy, TMR, ECC memory, and watchdog circuits. Components could be placed inside a radiation vault with core spares available for automated switch overs in case of system degradation. Storage systems would be distributed across isolated and shielded memory blocks capable of memory scrubbing and re-imaging from master firmware snapshots stored in ultra-hardened zones. Communications subsystem. The SX band transceivers and antennas would include redundant deployable designs. To resist micrometeoroid puncture, thin antennas could be shielded from mesh domes or made body mounted with redundancy. The amplifiers would obviously be radiant tolerant by design and mounted with heat sinks connected to the platform's thermal bus. All connectors and housings would be EMI shielded and epoxy free and vented for vacuum compatibility. Structural and deployable mechanisms. The HCOIS bus structure would most likely use carbon fiber composite trusses for low weight and thermal stability with titanium inserts, key stress points. These materials are well known for surviving both thermal cycling and launch-induced vibrations. Exposed structures would be wrapped in atomic oxygen-resistant coatings, particularly in LEO variants, and would include Whipple shield layers to absorb hypervelocity impacts. Deployables like antenna arms or radiator booms could be built with breakaway zones to minimize damage propagation and designed with dry, lubricated, vacuum-rated joints for fault tolerance actuation. Then you have your ground interface ports. The optical ground station, OGS interfaces, could include recessed ports protected by deployable dust and debris covers with internal thermal control to prevent condensation or misalignment. These apertures would be coated with anti-static AO-hardened materials, and the fiber or electrical connectors themselves would be pre-baked and sealed to avoid contamination. In summary, designing HCOIS isn't about building one resilient part at a time. It's about interdependent hardening. Radiation tolerance informs layout and redundancy. Debris shielding reshapes the mechanical layout, and environmental extremes from atomic oxygen to thermal gradients demands materials, coatings, and designs that are robust but precise. In every subsystem, trade-offs have to be made. But if done right, HCOIS wouldn't just survive in space, it would thrive. Who's gonna make all of this? It's crazy, it's insane, and it's a lot of components, a lot of design considerations, a lot of specifications, a lot of requirements, and a lot of manufacturing and designing. So who's gonna make all of this? This particular section is important for entrepreneurs and upcoming companies who are looking to extend their businesses towards space and establish themselves as pioneers of space tech. So let's take a thoughtful walk through the kind of supplier ecosystem that needs to emerge to support a satellite like HCOIS. This isn't just another telecom bird. It's a flying optical backbone, a data router in the sky. So the supplier landscape just can't be the usual suspect. We need a heritage and bleeding edge photonics, AI, and even quantum tech. First, think in layers: knowledge, capability, and intent. The landscape we need has to be built not just around what companies do, but what they understand and how quickly they can evolve. This means we need companies that deeply understand spaceflight. These are the integrators and platform builders. They know what survives launch, stress, vacuum, radiation, thermal shock. Their facilities are massive: clean rooms, vibration test beds, thermal vacuum chambers, mission control simulation bed labs, all of them are needed. Companies that live and breathe photonics, not just making lasers, but tuning, multiplexing, dynamically routing photons as if they were traffic packets. And these folks work in optics labs with femtosecond lasers, tunable filters, and photonic integrated circuits. Their clean rooms look more like those in chip fabs than aerospace hangars. And then you have your software-defined intelligent firms. not just embedded systems developers, but you have to think AI on the edge. You need teams that can write code for real-time anomaly detection, intelligent routing, compression, prioritization of mission-critical data. These companies build their own edge interface engines. They work with radiation-hardened AI chips and train on real mission data. So, the right kind of facilities. To serve HCOIS, we need supplier sites that blend space-rated hardware production with photonics lab capabilities. You have your vacuum-compatible optical bench assembly zones, you have your hybrid simulation facilities, and you have the quantum-safe clean zones, dynamic and static supply chains. So HCIOS isn't monolith, it's modular, upgradable, and built for change. So the supplier network also needs agile subsystem developers. They need to have standard compliant component makers. You need to also have ground infrastructure partners who would build optical ground stations that act more like optical switches or data center routers than just simple dumb terminals. And then now you look at the security-centric part of the design. In a system that will one day carry quantum keys and defense traffic and sovereign AI training data, suppliers must embed security into the hardware. Firms must prove that their trustworthiness is not just in supply chain terms, but in cryptographic handling, key management, and data flow isolation. Even optical pathways need enforcement mechanisms like filters that ensure EU-only routing when mandated. This creates demand for a new type of supplier, one that does data governance in photonic hardware. And then there is the interface layer. A lot of suppliers will never touch the satellite directly, but they will shape how it integrates with Earth. You need companies building multi-terabit optical splicing hubs where space links dovetail seamlessly into terrestrial fiber. You also need digital twin environments, firms building real-time simulators that model HCOIS links, ground station visibility, weather impacts, and data queuing. So network operators know exactly how to reroute during a storm in Tenerife. In summary, you're not just sourcing boxes and brackets, you're curating a multi-domain orchestra of spacecraft builders with decades of reliability, photonics labs that treat light with logic, AI and quantum specialists who see space as the next compute layer, security firms who design trust into optical paths, ground engineers who see the Earth-space interface as a fabric, not a seam, and perhaps most importantly, suppliers who aren't afraid to learn from one another. Let's walk through what those facilities of different suppliers should look like and should feel like. What kind of machines live inside them? When you're building something as boundary-pushing as the HCOIS satellite, what should you look for? Imagine stepping into a space that hums with quiet purpose, part precision engineering floor, part photonics laboratory, and part futuristic observatory. These are not cookie-cutter factories. They are ecosystems of capability. Here's what you would find in each kind of zone. The space-related hardware meets photonic precision. This is where aerospace tradition meets the precision of light. You're dealing with everything from high-tolerance mechanical mounts to flight-ready photonic chips. Machines and tools you would find here are 5-axis CNC milling machines with micrometer tolerances for building mounts and frames that don't warp in space. And you have your clean room optical benches with vibration isolation. These allow precise alignment of laser diodes, mirrors, and lenses. You should also have coordinate measuring machines, CMMs, to inspect sub-micron misalignments between components. Your wire bonding and die attach tools for packaging space-grade optoelectronics like your indium gallium arsenide photodiodes and laser drivers. Your thermal cycling chambers, which simulate rapid temperature swings from 100 degrees centigrade to 120 degrees centigrade. It's a place where engineers wear hairnets and latex gloves, not because it's fussy, but because dust or single human fingerprint can scatter a laser beam or misalign a quantum emitter. You have your vacuum-compatible optical assembly zones. Let's go to assembly now. Light behaves differently in air and space and is unforgiving in vacuum. Unforgiving in vacuum. So when you're designing an optical interconnect satellite, you can't assume performance in atmosphere, translating to performance in orbit. Machines and tools here include high vacuum chambers with optical feed-throughs, where you can test lasers, beam alignment, and photonic switches in vacuum. Then you have your precision alignment robots with nano positioning stages to automatically align fiber optic interfaces inside vacuum environments. And you have your UV laser micro machining stations to etch or tune photonic circuits in situ. Optical coherence tomography systems used to non-evasively inspect waveguides and lens assemblies down to nanometers. This zone blends surgical precision with space survivability. Think laser beam steering being tuned with a mirror the size of your pinky nail, all inside a chamber colder than Antarctica. Hybrid simulation environments. Before anything else flies, it gets simulated. But for HCOIS, traditional thermal structural tests aren't enough. You need to simulate the full experience. How photons propagate, how the satellite moves, how algorithms adapt on the fly. Such an environment should host optical channel emulators. These simulate how light would distort across 36,000 kilometers of atmosphere, including clouds, turbulence, and humidity. It should also have dynamic satellite motion rigs, tables that mimic optical slewing, vibration, and jitter, allowing optical terminals to prove that they can lock on under real conditions. And then you have your hardware-in-the-loop AI testers, where onboard FPGAs or neural chips are fed real-time beam telemetry and must-take decisions like rerouting or prioritizing the Earth stations. It's like having a flight simulator for photons, except this one also predicts weather, network congestion, and hardware faults. It runs faster than real-time. Quantum-safe assembly zones. Here, the air should be cleaner than an operating room and the temperature never fluctuates more than 1/10 of a degree. This is where the future-proof modules of HCOIS are born, entangled photon sources. So the QKD chips and single photon detectors, you would have to find ultra-clean ISO 1 or ISO 2 clean rooms for assembling delicate photonic crystals or waveguides with zero contamination. For the bleeding edge of quantum photonics, especially when you're fabricating and integrating single photon sources, entangled resonators, the requirements absolutely exceed ISO 1, ISO 4. Cryogenic test benches for characterizing and superconducting detectors or quantum memory elements. Single photon counting stations to verify QKD fidelity, timing jitter, and polarization stability. Quantum dot placement robots, which align nanocrystals with sub-100 nanometer precision onto chips. This is the cathedral of quiet science, where even the noise of a footstep is too much. Even every photon, every bit of quantum information has to be born in absolute control. For space applications, you're not building parts, you're weaving light, logic, and movement into a coherent space-worthy system. Each machine, each bench, each chamber becomes a collaborator in that process. That is all for now for this episode. See you in the upcoming episode where I'm going to talk about how a company could scale in their space tech business. Thank you.